Hey everyone. In this video, we're going to finish up our discussion of Chapter 16 material, this is dealing with coordination compounds, by discussing their electronic spectroscopy. So now we're going to be talking about the electron transitions that appear in these different types of systems. We're largely going to focus on octahedral since that is the most common geometry that we have for coordination compounds. After that, we're going to go ahead and dive into Chapter 17, which is dealing with reactions of coordination compounds. So let's go ahead and get started with our discussion of electronic spectroscopy. So the electronic spectra of coordination compounds is important in the study of these compounds because these are characteristic of many of our D-block metal complexes. So that is the colors that arise from them. UV-vis spectroscopy is what's used whenever we talk about electronic spectra of coordination compounds. And this is due, of course, because the energy difference in the orbitals, so the energy change for the electrons that are involved in these systems, end up appearing in typically the visible spectra. So this is one of the characteristics of our transition metal complexes or D-block metal complexes, and why they were and still are commonly used in pigments and dyes. So the UV-vis spectra of transition metal complexes will show, of course, the transition of the electrons that are in the system. On the right-hand side are typical characteristic spectra that we're going to obtain for the different electron configurations of D1 through D9 systems. But before we really get into looking at these individually, let's remind ourselves a little bit about the process of UV-vis spectra, spectrophotometry. So, electronic spectra are obtained using ultraviolet visible spectroscopy. Can also be referred to as spectrophotometry, depending upon whether you're counting number of photons that are passing through for a quantitative concentration dependent evaluation, or if we're just looking at the absorbance relative to wavelengths, which the latter is what we're going to focus on for this course and for what we're doing right now. The way these systems work then is, of course, we have a sample that's held in a cuvette, and we shine a light source through it. That light source has some incident intensity that's denoted as I naught, and we can measure that intensity when the sample cell is empty, and then also when we have our analyte in the sample cell, in order to see the difference between the intensity that actually gets to the detector. We have some set distance or set length, path length through which the light travels, which is denoted as L. This is typically 1 centimeter. And this gives us then the equation of A equal epsilon BC, or what's written on this slide is A equal epsilon LC, where L, or as I said a moment ago, B, is the path length through the solution in centimeters. Epsilon is the molar absorptivity, also referred to as the molar extinction coefficient. This is going to be dependent upon the actual nature of the electron transition, so the intensity associated with it. And then A is the absorbance. Absorbance, of course, is also related to the log of incident radiation over our radiation that passes through, or the intensity that passes through the sample. That could also be referred to as negative log of I over I naught. Of course, that's the same thing. In addition to that, of course, we understand E equal h nu, or E equal hc over lambda, where the energy of our photon is related to the Planck's constant times the frequency of light, where frequency of light is c over lambda, where c is, of course, the speed of light, and lambda is the wavelength. Very oftentimes, we're going to see our spectra obtained as plots of absorbance versus wavelength. However, we're also oftentimes going to encounter systems that express wave number, which is 1 over the wavelength in inverse centimeters. That's important, especially whenever we go to the quantification of our electronic spectra data as we move forward. So, the importance of our electronic spectra, first off, is that the electronic spectra provides us with a significant amount of information regarding the structure and bonding of our systems. So we've already talked about our crystal field theory and ligand field theory, and we understand that the identity of metal and the identity of ligand is going to have an impact on delta octahedral. That is the energy difference between our d orbitals in an octahedral field. So by looking at the electronic spectra, we can potentially identify what that energy difference actually is quantitatively. And then this can provide us with information regarding how these systems might react. Because, of course, we understand that the behavior of systems is dependent upon the frontier molecular orbitals, so the HOMO and the LUMO, or the SOMO of your systems. So it can be incredibly beneficial and incredibly informative for us to identify the electronic spectra, or to collect the electronic spectra of our systems. This can also help us to clearly identify oxidation states of different complexes. So if there's any question of oxidation state or high spin versus low spin systems. So our absorptions, of course, UV-Vis is necessarily an absorption technique, so absorption spectroscopy. Our absorptions are going to arise, of course, because of transitions between electronic energy levels. This is exactly equivalent to what we've discussed previously with regard to absorption spectroscopies. The different types of transitions we're going to observe, or in other words, the bands that we observe, the absorptions we observe, are going to be related to a few different types of phenomena. We're going to focus on three in particular, although there are a couple of others, transitions that are discussed in your textbook as well. The three that are listed here are the most common and the most important generally. The first is going to be the D to D transitions. So that's the transition between just the D orbitals on the metal. And these are generally going to be rather weak in intensity. And we'll talk about selection factors here in just a moment to examine why those D to D transitions are weak, whereas our ligand to metal charge transfer and metal to ligand, that is LMCT and MLCT, are quite intense. The energies that are associated with these different processes are necessarily different, though, so we can still evaluate these different transitions dependent upon what region of the spectra we're looking at. So, as I've already mentioned, UV-Vis spectra are useful because very oftentimes they're used to determine the octahedral splitting energy for a complex in, of course, an octahedral environment, which is what we're going to focus on. I should also note that the presence of electron-electron interactions can significantly complicate our spectra, just like our discussion of quantum mechanics, whenever we talk about electron configurations, these sorts of things. The presence of additional interactions, especially repulsive effects from electron-electron interactions, can lead to complications within the system. What that means then is that we're very oftentimes going to use a simplified version of our system and then explain deviations based upon some repulsive effect or some distortion that occurs within the system as well. Before we move on, what I want to go ahead and do is address selection rules for our electron transitions. So again, we're going to be focusing on octahedral complexes. And in our octahedral complexes are electronic transition selectivity rules. So our selectivity rules for our electron transitions. First is that they have to be G to U transitions. In other words, what that means, that's G to U or U to G. In other words, there must be a change in symmetry with respect to inversion. This is referred to as the Laporte selection rule. And this would, systems that, or transitions that obey the Laporte selection rule are referred to as orbitally allowed, or Laporte allowed. Our other selection rule is that we must maintain spin multiplicity. So this means that S, capital S, the change in capital S must be equal to 0. And systems that obey this are referred to as being spin allowed. So you can kind of tell that I'm about to inform you that there are systems in which we have spin disallowed transitions or orbitally unallowed transitions, or in other words, orbitally forbidden transitions. And that's absolutely true. So D to D transitions are weak because they're all Laporte forbidden, or in other words, orbitally forbidden. Whereas our ligand to metal transitions, ligand to metal charge transitions, and metal to ligand charge transitions are orbitally allowed, and they're also going to be spin allowed, those that are strong. We can then rank our strongest interactions, or the strongest intensities, which are going to be related to epsilon, so the highest molar absorptivity constant. We can rank these then if we have spin allowed and orbitally allowed are going to be the highest energy, followed by spin allowed, orbitally forbidden, then spin forbidden, orbitally allowed, and then lowest epsilon is going to be spin forbidden, orbitally forbidden. So now that we've gone over our selection rules, let's go ahead and move forward with our discussion and explain a little bit about how we might use electronic spectroscopy. So of course we mentioned that we can determine delta octahedral from our electronic spectra. If we take, for example, a D1 system, D1 system necessarily only has one allowed transition which can occur. This is going to be a transition from the T2G set of orbitals to the EG set of orbitals. So we can essentially directly read the energy of delta octahedral based upon the energy of this transition. Now you'll notice there is a toothed appearance, or a shoulder that appears on our band that's observed here. And that toothed appearance of the peak or of the band is due to a Jahn-Teller distortion of the excited state. Recall whenever we addressed Jahn-Teller distortions previously, that the strongest distortions are going to occur when we have a degeneracy in the EG star set of orbitals. So if we consider a transition where we have our T2G up to our EG star, we start off with an electron in the T2G, and then we have an excitation by H nu, which will give us an electron in our EG star set of orbitals. At this point, we have a degeneracy because our electron may reside in the z squared or the x squared minus y squared. So this can be followed then by a Jahn-Teller distortion, So this can be followed then by Ion-Teller distortion, and I'm just going to focus on the EG star since that's the one we're most interested in. And this will give us a stabilization in that EG star set of orbitals, providing us with this toothed appearance then. This is going to be a common feature that we observe. It's important to recall that a Ion-Teller distortion can occur anytime we have degeneracy in the EG star set of orbitals. So, let's go over some general observations for our different electron configurations. If we consider D1, D4, 6, and 9, these systems usually have just one absorption. Very oftentimes, though, we will observe a side toothed appearance or a shoulder on our bands that results from Ion-Teller distortions within those systems. One thing that I think is important to think about is if we consider D4 and D6, you might be inclined at this point to ask, well, do D4 and D6 always only occur? Do D4 and D6 always only result in the one transition, or is there a dependence of high spin and low spin? I think it's important that you should draw out the electron configurations for both a high spin D4 and D6 system and low spin D4 and D6 systems, and prove to yourself that in fact there is only one spin allowed transition for any of those systems, such that we would still only expect to observe one transition. If we look at D2, D3, D7, and D8 systems, these usually have 3 absorptions, although one of them is very oftentimes obscured by charge transfer bands. So again, I mentioned that our ligand to metal charge transfer and metal to ligand charge transfers are going to be of significantly greater intensity. And when we start getting to higher energies, very oftentimes we're going to observe a charge transfer that's going to basically bury our D to D transition instead. So we have to be careful about our interpretation. We can't necessarily make claims about the electron configuration just based upon the number of bands that are observed. We instead have to think critically and chemically about our system to be able to evaluate what's going on. For D5 complexes, these consist of incredibly weak and relatively sharp transitions because these are spin forbidden. So therefore they have incredibly low intensities. We're already talking about D to D transitions, so these are Laporte forbidden or orbitally forbidden. And then if we tack on top of that the fact that we have a D5 system, these are now spin forbidden as well. So let's consider back to our systems where we have 3 bands that are observed. So in particular, when we looked at our D2, D3, D7, and D8 systems, let's consider a chromium-3 complex. So let's look at hexaamine chromium-3 and try to justify why we would observe 3 bands in that system. So our ground state electron configuration for a chromium-3 complex, of course, is going to be a T2G3 electron configuration. In this situation, we have the possibility in which a transition could occur from DXY, DYZ, or DXZ. And then we could go to either DZ squared or DX squared minus Y squared. In terms of just the overall energies of the system, we of course know that all 3 of our T2G set of orbitals are degenerate with one another, and our 2 EG star orbitals are also degenerate with one another. However, there's still a difference in terms of the environmental change. So for instance, a transition from dxy to dx squared minus y squared is not a very substantial change in terms of through space. We essentially, in order to accommodate that transition or have that change in environment, we could think of shifting our orbital by 45 degrees. This would generate, of course, dx squared minus y squared if we started from dxy. Similarly, dyz and dxz transition to dz squared also involves a relatively minor change. Let's look at this a little more closely. So if we look at a transition of dxz to dz squared, again, the region of space, the volume that's occupied by our dxz orbital is nearer to the dz squared orbital. Whereas if we consider a system where we have dx squared minus y squared transitioning to dz squared, there's a much more substantial change in the electronic environment for that system. So this is just kind of a qualitative approach to explain how those transitions might occur. So since that promotion of an electron from T2G to the EG star can involve multiple changes in environment, we're going to see several peaks or several bands within that system. Collectively, these are related to our electron configuration change of T2G3 to T2G2 EG1. However, if we break this down to molecular term symbols, which are akin to our atomic term symbols, we actually can have transitions to two different states within that system. And we're not going to go into detail about how to identify what these molecular term symbols are, but just going to note that T1G quartet is different from a T2G quartet. And we're not going to go into more detail than that. These are symbols that are derived from the direct products of irreducible representations, or in other words, Mulliken symbols. But again, that's beyond the scope of this course. So if we consider some other systems, something that would apparently be quite simple, D9 system, we of course expect that there's only one D to D transition. This is going to be a conversion from a T2G6 EG3 electron configuration to a T2G5 EG4 electron configuration. If we deconvolute the electronic spectra, we can actually identify three D to D transitions for this copper-2 complex. A way that we can explain that then is related to Jahn-Teller distortions. So if we have a tetragonal distortion, that is an axial distortion, which is an elongation of those axial bonds, we can observe that there are now three different energy states that can be achieved. So three different excited states that are within that system. From a quantitative standpoint, we can use what are referred to as Tanabe-Sagana diagrams, or TS diagrams. Our Tanabe-Sagana diagrams are essentially a specialized correlation diagram that's used by spectroscopists in order to identify the energy difference in orbitals within octahedral systems. Now, these can be quite complicated to work with, and we're not going to go into great detail with them. I'm going to go over some of the basics. Your book actually does a really phenomenal job about with regard to how to calculate the d orbital splitting energy, so delta octahedral, by using Tanabe-Sagana diagrams. What I'm going to emphasize right now are just how to read a Tanabe-Sugano diagram and how to identify the number of expected bands based upon the electronic configuration of your system. So, a few different things that I want you to note. We first will note the axes. On the x-axis, we have delta octahedral over B. In this case, it's just denoted as delta, but these are for octahedral complexes. So we have delta octahedral over B, where B is referred to as a Rakaw parameter. So B equals Rakaw parameter. And it's a term that's going to be useful as we move forward and gets incorporated into evaluating some other properties about our systems as well. In particular, it's going to be directly related to the extent of covalent character in our system. You'll notice on the y-axis then we have energy also divided by this Rakaw parameter B, or the B Rakaw parameter. Each of the lines that are shown here indicates a particular molecular term symbol. And this will be a given state that's provided. On the far left-hand side, we have atomic term symbols that originate, from which the molecular term symbols originate. So the atomic term symbols are the same as what we've worked with previously at the beginning of the semester, beginning of this course. You'll also notice that the x-axis, we have a baseline term symbol for the entirety of this. And if you focus on the D3 system right now, we see that we have a quartet A2 ground state. All of your other states are given with respect to this ground state term symbol. So in other words, the energy that we note on the left-hand side, the vertical axis, is relative energy with respect to your ground state. Now, if you turn your attention to the D4 system, you'll notice that on the left-hand side of a vertical line, we have a pentet E ground state, but then as you cross this line, the ground state changes. So pentet E goes to a higher energy, and it's now an excited state. All of the lines that are above, or all the states that are above the ground state, aren't necessarily excited states, of course. And our ground state to the right-hand side of this vertical line is now a triplet T1 ground state. Now, this indicates then that we have a low spin environment on the right-hand side of this vertical line and a high spin environment on the left-hand side of our vertical line. So this vertical line, in this case at a delta octahedral over B of approximately 2.8, indicates where we have the transition from high spin to low spin. When delta octahedral over B is greater than, in this case, approximately 2.8, then we end up going into the low spin environment. That necessarily means there are different electronic excited states that are allowed, or in other words, there are different electronic transitions that are expected to be observed. Now, if we think back to our selection rules, we understand, first off, of course, we have the port selection rule that says that for a transition to be intense, that it must change its symmetry with respect to the inversion center. However, all of our D to D transitions are Laporte forbidden, so we're not going to worry about that right now. The second selection rule that we had was that the total spin of our system, so the total multiplicity of our system, must not change. What that means then is that our allowed transitions our spin allowed transitions, are only those that maintain the same multiplicity. If we look at our term symbols, again, our multiplicity is shown as a superscript to the left of our term symbol. So, if we look at our D3 system, we have a quartet A2 ground state. In order to identify the number of allowed transitions or expected transitions, all we have to do is look at the multiplicities for all of our excited state terms. The first excited state that we encounter is a quartet T2, and it remains the first excited state regardless of what the delta octahedral value is. Our second excited state, regardless of what delta octahedral is quartet T1, and then our third allowed excited state is going to be quartet T1. So we have two quartet T1s for our excited state systems. And you can tell then that we would expect to observe three different electronic transitions, so from ground state to excited state, for a D3 system. Necessarily, these would occur at some particular value of delta over B. So let's say that we have some value here, and we would expect these three transitions. Coming up in a little bit, I'll talk a little bit about how we can actually quantify delta octahedral, but that's not really the purpose of this section for this course. That's a bit beyond the scope of what we're going to do. I do recommend that you take a look at it in your textbook. Again, your book does a great job of evaluating or showing how to evaluate quantitatively Tanabe-Sagana diagrams. If we look at a different example, let's consider a D5 system. So on the far right-hand side, in our high spin environment, we have a sextet A1, so a multiplicity of 6. And you'll notice that there are no excited states that are also sextet. This is obvious. If we consider what it takes to have a multiplicity of 6, we have to have 5 unpaired electrons. That's necessarily T2G3 Eg2. So that's necessarily T2G3 Eg2, which means that there are no spin-allowed electron transitions. All of our excited states will necessarily involve a change in spin or spin multiplicity. If we look at our low spin system, though, this is a doublet electron configuration. So this is high spin on the left. If we look at a low spin system, 1, 2, 3, 4, 5, this doublet, we have doublet T1 excited state, doublet A2, doublet E2, doublet A1 excited states. So we have 4 different excited states that we can achieve in the low spin system. So I'll talk a little bit about how we can use our experimental UV-Vis data and a Tanabe-Sagana diagram in order to determine our d orbital splitting in octahedral complexes. Basically, what we can do is first off convert our energies of our transitions to wave numbers. If we then look at the ratio of our transitions, so the energy of those different transitions, so in this case, let's say V2 over V1. So we can identify the ratio of the energies of our transitions. In this case, we have 25,600 over 17,200, which gives us a ratio of 1.49. We can then use a ruler to go across our Tanabe-Sagana diagram and evaluate at different positions what are the energies of our allowed transitions. So for instance, what I've marked so far at delta octahedral over B, in here, in this case it's denoted as delta octahedral prime, but it's delta octahedral over B of 10, we have energies of about 18 over about 9. So in that case, we would have a ratio of those transitions of about 2, which would indicate, of course, that this is not the appropriate value of delta octahedral over B. If instead we look at where the arrows were originally marked on here, so those that are marked in black, and we can evaluate then the energies of these transitions, we have approximately 32 and approximately, let's say, 19 or so. It's not perfect. My estimations here probably aren't all that great, but we get a value that's nearer to our ratio. You see then that this isn't necessarily exact, and it can be quite complicated to work with these Tanabe-Sugano diagrams, which again is why this is not going to be the focus as we move forward, but it helps give you an idea associated with it. Once we've gone through and we've identified delta octahedral over B, so in this case we'll say delta O over B is equal to, let's call that 21.5. We can then look at the energies associated with these transitions. So if we have E over B is equal to 19.5 or so, so we'll say E over B, so E1 over B is equal to about 19.5. We know that the energy of this transition, E1, is actually equal to 17,200 wave numbers. Substituting in the value of E1 and using our determined value of delta octahedral over B, and using our determined value of E1 over B of 19.5, we can then determine the value of the Rakoff parameter B. Once we've determined the value of B, we can go back and solve for our delta octahedral using that initial X term that we've identified too. I'm not going to expect you to do all of this. I think that it's useful for you to understand how we can use this information. I also think it's kind of fun. This is another one of those puzzles that's introduced. I mean, puzzles is basically why I'm involved in chemical research. So I hope that you find this interesting. I hope that you find it helpful. But if you have particular difficulties with this, don't worry too much about it. It's not that big of an issue. In fact, if you don't become an inorganic chemist or a spectroscopist, there's a good chance you're never going to see a Tanabe-Sugano diagram again. But, again, it's another thought exercise, something to stimulate the mind and serve as a bit of a puzzle. I'm happy to talk to any of you more about this as well, but for right now, we're going to go ahead and move on. There are a few other examples that I have in these slides, but we're going to kind of just slide past those. So, again, if you are interested and you want to play around with them, have at it. There are a number of examples that are provided here, and you can also observe the effects of different ligands. In particular, in these cases, we have essentially a variety of sigma donor ligands, and then we have water is going to behave as a slight pi donor, whereas pyridine and bipyridine will be slight pi acceptors. You can see then too how the transitions go to higher wave numbers, in other words, higher energies, as the strength of the pi acceptor increases. So again, water being slightly pi donating, we have smaller energies for those transitions. Pi donor, again, is weak field ligand, resulting in a decrease in delta octahedral. Whereas our aromatic systems, those that have accessible pi star orbitals, are going to be pi acceptor ligands, that results in a stabilization of the T2G set of orbitals and an increase in delta octahedral. This is the bigger concept that I want you to understand out of all of this. If we evaluate the trends in terms of the energetics of our transitions as related to the identity of our metals and identity of our ligands, that's what I want you to be able to explain. So use your knowledge of ligand field theory, use your knowledge of oxidation states of your metals, and the behavior of ligands in order to explain the different trends. This example in particular does a great job of exhibiting chromium versus manganese versus molybdenum, all with the same ligand, and then also evaluating the ligand effects on your chromium system. So look at these, make sure that you understand where the trends are coming from, regardless of whether you want to go through and actually solve delta octahedral for any of these systems. Okay, so that really finishes up what I wanted to cover with regard to spectroscopy of coordination complexes. That's going to finish up our chapter 16 material, and coming up next then, we're going to go ahead and jump into talking about reactions. So the primary reaction pathways that we're going to discuss in coordination chemistry are those of substitution reactions, electron transfer reactions, oxidative addition, and reductive elimination. And we're going to look at each of these independently as we move forward. So this is just kind of an outline of the topics that we'll be addressing as we go through this. Let's start off with the discussion of ligand substitution reactions. These are pretty straightforward. So if we consider we have some leading group X and some entering group Y, we can evaluate the process as ML some number of ligands, X plus Y goes to form ML sub number of ligands, Y plus X. Again, just the typical notation that we use for this. X is a leaving group comparable to what we had in organic chemistry, and then Y is the entering group. We classify the types of metal complexes as either labile or inert. So those metal complexes that undergo substitution reactions with a half-life of less than 1 minute at 25 degrees Celsius are called labile. And those with half-lives that are greater than 1 minute are termed inert. This is strictly a kinetic effect. So as with everything in terms of reactions in chemistry, we have to consider both the kinetics of the reaction as well as the thermodynamics. If you recall from your discussion of mechanisms previously or reaction diagrams previously, we understand that the thermodynamics of a process is just related to the initial and final states of our systems. So the energy that's transferred in that system or in that reaction. The kinetics, however, are dictated by the activation energy, so the activation barrier that must be overcome in order to move from reactants products. So an example would be if we have hexaamine cobalt 3 in an acidic solution, so adding 6H3O plus to it, we'll produce the hexa-aqua cobalt 3 and 6 ammonium ions. The equilibrium constant associated with this is about 10 to the 25th. This means it's an incredibly product-favored reaction. If you recall, delta G naught of reactions related to negative RT ln Q. So this is a highly exergonic reaction, meaning that it's spontaneous. However, spontaneity has nothing to do with the kinetics of the process or how fast a process will occur. We find that hexaamine cobalt 3 will actually persist in acidic solution for days. Therefore, we would say that hexaamine cobalt 3 is an inert metal complex. All right, so to go over a few rules with respect to our inert and labile complexes. First is that all ions of the first transition metal series, as well as the lanthanides, are labile, except for chromium-3 and low-spin cobalt-3. So that gives you information with respect to hexaamine cobalt-3 and indicates that this is in fact a low-spin complex. Low-spin complexes tend to be less labile than high-spin complexes of the first transition metal series. And then all ions of second and third transition metal series are inert except for D0 and D10 systems. So to look at the different types of mechanisms that are associated with our octahedral substitution reactions, we can look at these coordinate diagrams and evaluate three different mechanisms. We have the associative mechanism, in which case we have an entering group that comes in and forms a intermediate in which both our entering group and leaving group are connected. We then have a second activation energy in order for our leaving group to leave the metal complex. And we have an interchange mechanism, which is going to be intermediate between dissociative and associative. Interchange, essentially, our entering group and leaving group are forming and breaking bonds respectively at the same time, such that there's not really an intermediate that can be identified. And then the other is a dissociative mechanism. And in dissociative mechanism, we have the leaving group will break its bond first and leave the metal complex. We then have an intermediate in which our metal complex is only 5 coordinate, and then our entering group will come in and form our final product. We can think of associative mechanisms, associative mechanisms and interchange mechanisms, kind of comparably to our SN2 type of reactions. SN2 reaction in organic chemistry probably is most closely associated with an interchange type of mechanism. And our dissociative mechanism is akin to an SN1 reaction, where we would have the formation of a carbocation, and then an entering group comes and fills the empty position that was made available. Except, of course, now we're talking about a coordination complex. When we consider our octahedral substitution reactions, then we can talk about the different factors that can impact our mechanism. And this is, of course, going to be related to the reaction rates. So the concentration of our entering group Y, as we increase the concentration of Y, we increase the likelihood of an associative mechanism. So basically, if you flood the reaction area with your entering group, it's more likely the entering group is going to associate to the complex prior to a dissociation. Dissociative mechanisms show little dependence on the presence of your entering group or identity of your entering group. As we increase the nucleophilicity of the entering group, we have an increased likelihood of an associative mechanism, and comparably then, as we have weaker MX bonds, so as your leaving group has a weaker interaction with the central metal, we're going to favor a dissociative mechanism. Sterics can also play a significant role. So for instance, if we have large ligands L that make our metal complex sterically hindered, then it's much less likely to form a 7-coordinate system, which is what we would necessarily achieve from an associative mechanism. A question that I have posed on here then, and I want you to consider for a bit, is what effects do chelating agents have on reaction rates? So if you consider something like ethylene diamine, how would the reaction rate of exchanging ethylene diamine with 2 ammonia molecules be affected? Well, if we consider ethylene diamine versus ammonia, so we have some metal complex, and if this is ethylene diamine And the other ligands, I don't care. They're just call them L. And let's say that we're going to substitute 2 ammonias. The first thing I'm going to note is that the ligand behavior is going to be quite comparable. Both ethylene diamine and ammonia are going to have similar sigma donor properties, and they're also sigma only donors. If we consider this process, though, we see that we necessarily are going to have to break 2 metal ligand bonds in order to isolate these sites on our metal complex. If we have just the breakage of one of those bonds, we still have this dangling ethylene diamine species. And if we consider this open site, I'm going to note with just an orbital right now, if we consider whether we have an ammonia molecule come in and coordinate to that site, or this other end of the ethylene diamine come and coordinate to that site again. Well, the other end of our ethylene diamine is already closer in proximity to this open metal site, and it's in fact tethered to our metal site by the other end of it, that it becomes less likely that ammonia is actually going to substitute in here. This substantially slows down the kinetics of this exchange process, or the substitution process then. So this is referred to as the chelate effect. And that's just as related to kinetics of a substitution process because of that close proximity due to the tethering. Let's look at substitution reactions in square planar complexes next then. All square planar substitution reactions are necessarily going to be associative. This should intuitively make sense because we have essentially open sites at the top and bottom of our square plane. So what can happen in those types of situations, if we have let's say 3 of these are L, and then we have a leaving group X. You can have some entering group Y that comes in and coordinates onto this top face. This will give us a 5-coordinate system that's square pyramidal. Followed by, we have a reorganization of our system. So Y is going to move into this new equatorial position, pushing this X into an axial position. And then finally, we have the breakage of that bond to give us our new square planar system. We also have some interesting behavior dependent on the identity of the neighbor that's trans to the position that's being added. So what I mean by that, So this is referred to as the trans effect. We have what are called trans-directing agents or trans-directing strength that's related to the destabilization of our starting materials. So that's going to be strong sigma donors, and then comparably a stabilization of the transition state, which are going to be our strong pi acceptors. So we can see the strength of trans-directing agents are as follows on the system that we have shown below. Fluoride, water, hydroxide are all weak trans-directing agents, whereas the hydride anion, H-, which is an incredibly strong sigma donor, cyanide, which is a good pi acceptor, a strong pi acceptor, these are going to be strong trans-directing agents. We can predict the product that's formed from these systems then based upon evaluating our system, the organization that we have here. And taking advantage of this trans-directing strength is important in the preparation of, in particular, cisplatin, as we have denoted on the right-hand side here. So we can get a diamine dichloroplatinum 2 species that's either cis or trans, depending upon whether we start with the tetrachloroplatinate, so tetrachloroplatinate 2, or the tetraamine platinum 2 complex. If we start with tetrachloroplatinate 2, we add ammonia to this system, the first ammonia that adds doesn't matter in which position we add it. All of the chlorines are the same. Our second platinum, though, is our second ammonia necessarily will be added trans to one of our chlorides, though. So chloride is a stronger trans-directing agent than ammonia. And the reason for this is that chloride is a better sigma donor than ammonia. So this gives us our diamine dichloroplatinum 2. If, on the other hand, we start with tetraamine platinum 2 and we substitute chlorides for ammonias, the first chloride, of course, again, doesn't matter where it's added, but the second chloride will add trans to the first chloride. So this necessarily gives us trans diamine dichloroplatinum 2. The next type of reactions we're going to talk about then are electron transfer reactions. We'll refer to these as ET reactions. ET reactions are necessarily redox reactions between two coordination compounds. These may occur between the same metal with different oxidation states, so this is referred to as a self-exchange reaction, or this may occur with different metals, which is referred to as a cross reaction. The way that we can monitor our self-reactions, this should actually be an ammonia. Our self-reactions, in this case, is if we use radio labeling. So we have a particular isotope of cobalt radio labeled, so we can follow the oxidation state change within that system. In addition to our self-reactions and cross-reactions, we also have two other distinguishing features of electron transfer reactions. These may be inner sphere electron transfer reactions or outer sphere electron transfer reactions. Our inner sphere ET reactions involve exchange of ligands. So inner sphere, again, noting our coordination complex within the brackets is our inner sphere. And this necessarily then is going to change the identity of ligands that are present in that inner sphere. Whereas our outer sphere electron transfer reactions, there will be no exchange of ligands. Let's look a little closer at these two different types of ET reactions then. So our inner sphere ET reactions involve formation of bridged intermediates that help induce the electron transfer. And then we also have the transfer of the ligand that goes along with it. Generally, this is going to involve one labile and one inert species. If we consider the classic example shown in the top right, then we have hexa-aqua chromium 2 species, which is labile, and we have the pentaamine X cobalt 3 complex. In the presence of acid, we have the transfer of this X ligand, which is necessarily going to be a bridging ligand. So something that has at least two lone pairs that are on it. To follow this reaction mechanism then, we necessarily are going to have the formation of this reactive intermediate where X serves as a bridge between the chromium and the cobalt in order to facilitate the electron transfer process. So if we look at the step-by-step process involved in this mechanism, our first thing that occurs is that we have a water that leaves our chromium 2 as the X species bridges between the cobalt and chromium. Once we have our bridged intermediate, we can then have the electron transfer process take place. So electron transfer is going to result in a weakening of the cobalt X bond and the reinsertion of water onto our cobalt species now. So we have X is transferred over to chromium, and water is transferred over to the cobalt, in addition to the transfer of one electron from chromium to cobalt. And then lastly, because of the nature of this cobalt complex, we then have the exchange of our amines for water. And this has to deal with the cobalt 2 now being a labile system, and this reaction proceeds quite quickly in terms of the exchange of amine for water. Outer sphere ET reactions will necessarily involve no change in the chemical composition of the systems and will almost always involve inert species for both of the complexes. We can also have reactions that are outer sphere electron transfer in the event that we have labile systems, but there's no bridging ligands. So if only one reactant is inert and the other is labile, but there are no bridging ligands, then we can still have outer sphere electron transfer reactions that occur, because of course we can't form that bridged intermediate. To take a closer look at different types of electron transfer reactions, or different conditions we can have for different electron transfer reactions, let's consider the two examples shown here, where we have hexammine cobalt 3 and hexammine cobalt 2. So we have the self-exchange reaction involving hexammine cobalt systems, and then the same kind of self-exchange occurring with ruthenium systems. What we find is that the ruthenium reaction is substantially faster than our cobalt reaction. And a way that we can justify this is based upon the change in electron configuration as we have an electron transfer process. In our system, in which we go from cobalt 2 to cobalt 3, we're starting off in a high spin cobalt 2 system. So this is a high spin D7, where we have 3 unpaired electrons, giving us a multiplicity of 4. Upon the oxidation of cobalt 2, we go now into a low spin D6 system. This change in energy levels results in a significant change in bond lengths as well, and makes this process much slower as compared to the ruthenium process, considering that ruthenium 2 is a low spin D6 complex. When it's oxidized, it goes to a low spin D5. So the overall electronic change that you have in the ruthenium complex, since you start as low spin already, is much less substantial than what we observe for the cobalt system. This finishes up the material that I want to cover with regards to your coordination complex reactions, or typical inorganic coordination complex reactions. Coming up in the last video that we have for this course, so the next video, is going to be talking about organometallic complexes. So that's going to be systems that necessarily involve direct metal-carbon bonds, and then also organometallic reactions, which are particularly important whenever we talk about catalytic cycles. So until then, make sure that you're studying up on the material we've covered, and let me know if you have any questions.